I'm Suzanne Armstrong, Executive Director of World Discoveries, and will be your host today. I'd like to start with our event with a land acknowledgement, recognizing that this is a virtual event and we have attendees from a range of locations. The land acknowledgement I'm giving today is representative of the land I'm located on in London, Ontario. I invite each of you to respectively reflect and acknowledge the land you're located on today. I acknowledge that Western University is located on the traditional territories of Anishinaabe, Haudenosaunee, Lenape, and Chinookton nations, on lands connected with London Township and Sombra Treaties of 1796 and Dish with One Spoon Covenant Wampum. This land continues to be home to diverse Indigenous peoples whom we recognize as contemporary stewards of the land and vital contributors to our society. We're gathered today to launch the 7th year of this competition alongside our founding and competition partners, which include Tech Alliance, Western Research Park, and Western Morissette Institute for Entrepreneurship, and our Ontario universities such as University of Guelph, McMaster, Windsor, and University of Waterloo. I'd like to thank our collaborators and partners who have been working with us to bring this year's competition to our innovative and entrepreneurial communities. Also, a big shout out to our sponsors, whose financial contributions to the event provide the prize for the winners of the competition. This competition is structured as a 4-month-long journey for our competitors, where individuals are challenged to create a viable commercialization strategy for one of the 5 promising technologies showcased this year. Following the launch event, the contestants are asked to form their teams and submit their abstract by January 10th. The selected teams will then be invited to a virtual business plan workshop, and the teams with the best business plan will be asked to participate in the live virtual pitch event on March 31st for a chance to win $5,000 per technology. We're looking forward to the engagement we will be having with this community of competitors over the next 4 months. At this point, I'd like to invite Western University's President, Dr. Alan Shepard, to say a few words. Alan, you're muted.
Had to do that at least once. Good afternoon, everybody, and welcome to this version of Proteus. I think this is the 7th year, I believe it is, and proof of a winning formula for sure. And what started 6 years ago is now a province-wide initiative. I wanted to say also a special welcome to 3 people who are civic leaders amongst us: Jeff Urick, MPP, Peter Fragiskatos, MP, and Christina Fox, the CEO of Tech Alliance. Thank you for making time in your busy calendars to be with us today. So Proteus is all about leveraging the power of research and innovation to drive economic development through entrepreneurship and commercialization. I'm particularly excited by the way an event or a series of events, as Suzanne has just outlined, nurtures the entrepreneurial spirit amongst our students and researchers. It's also a wonderful opportunity to showcase some of the research coming out of Ontario universities. Previous competitions have seen some new companies being formed and technologies brought to market. Looking forward to seeing the results that will emerge from this year's contest. I hope I'm back in March to see how things have turned out. I'd like to thank all of our institutional partners and technology innovators for their contributions. I'd like to wish very good luck to all the people who are competing in this process. Thank you for participating, and welcome and good luck to you all. Thanks, Suzanne.
Thank you. Thank you, Dr. Shepard. Now, please join me in welcoming Honourable Jeff Urick, MPP, Elgin, Middlesex, London, and current Parliamentary Assistant to the Minister of Economic Development, Job Creation and Trade.
Yeah, thanks very much, and good afternoon, everybody, and thank you very much, Suzanne, for the introduction. And you know, I'm really proud that such an esteemed competition is put together, bringing together all the bright minds and ideas from across southwestern Ontario, and it's really including our great institution, Western University. You know, now more than ever, it's critical that we prioritize technological advancement as a means of increasing productivity, creating new revenue opportunities, as well as highly skilled jobs, while enhancing our global competitiveness for Ontario businesses. It's initiatives like these that drive the innovation that will fuel the province's economic recovery post-COVID-19, but also pave the way for a prosperous future. The efforts that will be undertaken during this competition will also showcase the eminence of Ontario's post-secondary institutions and uphold our proud legacy of academic excellence. These are all the things that make me incredibly proud as both a local member of provincial parliament, but also the parliamentary assistant to the Ontario's Minister of Economic Development, Job Creation and Trade. I would like to take the opportunity to thank all the partners and sponsors behind this exciting initiative and extend my best wishes to all the participants. You are representing Team Ontario very well, and everyone should be proud. So thanks again, stay safe, and hope to see you all soon.
Thank you kindly for your inspiring words. I'd like to invite Christina Fox, CEO of Tech Alliance, one of our longstanding partners, to introduce our next guest.
Good afternoon, everyone. I wanted to share with you the Tech Alliance is the place for dreamers, innovators, and world-changing ideas. And as a regional innovation center for Southwestern Ontario, we empower world-class ventures and fuel growth in Canada's innovation economy. And we champion and coach entrepreneurs and amplify businesses, creating a vibrant technology community. In partnership with World Discoveries, we aim to grow and strengthen collaborative experiences between academics and commerce, research and business, institutions, and community for the benefit of all. So it's always a joy to join this launch event each year because we have deep roots with this competition. Proteus was founded in partnership with Tech Alliance, and it's a perfect example of what can happen when collaboration is prioritized and when we work together to support researchers, students, and entrepreneurs in higher education across Ontario. So continuing to build momentum is a vital resource for technology innovators, tech talent, and industry leaders. Our team knows that challenging times, as we've seen over the last couple of years, bring exceptional people together. You are among them. We believe that collaboration is fundamental to every part of Proteus, from the planning team that has organized each element of the competition to the commercialization or tech transfer offices and researchers at each of the partnering institutions. So to the many supporters and sponsors, we thank you for playing a vital role in this competition. For the competitors, the chance to win one of the cash prizes is an obvious draw, but I know that you also see this as a terrific opportunity to learn more about launching a startup by creating a business plan, protecting intellectual property, and turning your business, your opportunity into a business venture. It's because you have world-changing ideas and ambition, coupled with the expertise of the partners that you've already experienced that positive collision of entrepreneurship and research. So my best wishes to each of you throughout the competition. And now it gives me great pleasure to introduce my friend, Member of Parliament, Peter Fragiskatos. As a valued Western alumnus, Peter was elected to represent the riding of London North Centre in the House of Commons of Canada in the 2015 federal election. A former political scientist at King's University College at Western, Peter is now combining his passion for politics with the drive to serve his community. Peter.
Very kind introduction, Christina. I'm overrated and you make me look good here. So thank you very much. And on a more serious note, thank you for your leadership in the community, really to see the work that Tech Alliance is doing. It's very heartening, particularly as we try to overcome the economic impact of the pandemic. And so I certainly share your sentiment. I share the sentiment of my friend Jeff Urich and of President Shepherd. Wonderful to take part again in Proteus in this great competition where it's a celebration of learning, celebration of ideas, ideas that have economic implications or certainly have the potential to. So we have a passion for business that drives all of this. And I go back to this point about COVID-19. The impact of the pandemic on our economy has been, it's obvious, but also it's something that's going to remain with us. And so I think universities have a key role in this. Our students have a key role in this as drivers of ideas and of learning, and World Discoveries as well. Thank you very much, Suzanne, and to everyone at World Discoveries, a key incubator for all of these things. And we need all the support we can get. Government will take us so far, but only so far. The role of civil society, and I use that phrase widely to capture as many as possible, includes everybody involved in this great competition. It's wonderful to see, and I know a lot of great things have already come out of previous competitions. I know that will be the exact same case here. So thank you again for the invitation.
Thank you very much, Peter and Christina. So 5 technologies, one from each tech transfer office of our partnered institutions, have been selected to be considered by the contestants for this competition. We'll be inviting the inventors of each technology to talk about their invention over the next 25 minutes, and the attendees will have a chance to interact with the inventors and ask questions at the breakout sessions after the presentations. Please note that the winning teams have the opportunity to help commercialize the technologies in collaboration with the respective TTO offices if they're interested to do so. I would like to welcome Dr. Aaron So, Assistant Professor of Medical Biophysics at Western University and Lawson scientist, who will be talking about his technology titled Dynamic Cardiovascular Imaging for Rapid Patient Treatment Planning. I'm going to stop sharing so Aaron, you can actually share.
Okay. Can you see my screen?
Yeah.
And let me start. Thank you, Suzanne, for the introduction, and thank you very much for inviting me to this wonderful competition. So today I'm going to present a new cardiovascular imaging technology that can be used for rapid patient treatment planning. But because of the limited time, I'm going to focus on only one specific application on coronary artery disease. Coronary artery disease is one of the leading causes of death, not only in Canada, but also in many countries in the world. The disease is caused by the formation of atherosclerotic plaque in the coronary arteries. Now, because the plaque narrows the arterial lumen, the blood flow to the heart muscle is affected. The choice of treatment for CAD patients largely depends on whether the blood flow reduction reaches a functionally significant level. Now, in order to determine whether a coronary narrowing or stenosis is functionally significant, the current gold standard test is performed in a cardiac catheterization lab, where the doctors will put in a pressure wire into the narrow coronary artery to measure the flow pressure gradient across the narrow segment. As you can see in the diagram on the right, the parameter measured with this procedure is called the fractional flow reserve, or FFR, which is defined as the flow pressure distal to the flow pressure proximal to a narrow segment. Now, an FFR value of 1 means there is no drop in flow pressure due to the narrowing, so it's all good. An FFR value less than 0.8 means there is more than 20% drop in flow pressure because of the narrowing, and it is generally considered as functionally significant. So if a vessel is associated with a FFR less than 0.8, likely the doctors will do further interventional procedure for treatment, such as placing a stent to keep the vessel reopened. Now, while this diagnostic test is the gold standard, clinically speaking, but several studies in the past have indicated that many patients referred for cardiac catheterization actually did not have significant stenosis. And for this reason, the current clinical guideline recommend the use of non-invasive functional tests as the gatekeeper to make sure we only send the most appropriate patients to the cath lab. And this is where our new technology can help. We have developed a new imaging technology using CT for non-invasive FFR measurement. Now, the reason why we choose CT is because CT, first of all, is invasive, and it has several advantages over other existing imaging modalities. For example, it is highly accessible. Almost every hospital has a CT scanner. It generates very high spatial resolution images, and a CT test is very fast. Now, this slide shows how our imaging technology works. We first inject a very small amount of contrast solution into the patient's vein in order to increase the signal of blood in the CT picture. Then we take multiple CT images of the heart in quick succession. And from these dynamic CT images, we can monitor the movement of the contrast solution in each coronary arteries. We have developed novel algorithms to calculate the absolute flow velocity and flow pressure at each point in each coronary artery based on the movement of the contrast solution in the coronary arteries. And I'm going to show you one example how our technology can be applied in real-world setting. This is a 68-year-old female who had a 40% coronary narrowing in one of the coronary arteries called the left anterior descending artery, or LAD. So the doctors send the patient to the cath lab, and the image on the right is another picture taken in the cath lab of the same artery, confirming the narrowing in the LAD artery. Now, because the patient was in the cath lab, so the doctors also place a pressure wire to measure the FFR and find it to be 0.93. So this narrowing was non-significant according to the FFR measurement. Now, this video, I'm going to show you how we can use our prototype software to analyze the dynamic CT images of the same patient to estimate the FFR non-invasively. So the user only needs to define the pre-stenosis and the post-stenosis sampling site and enter just a few pieces of information that can be acquired easily. And then the program will do the rest to compute the FFR for this specific coronary artery. So you can see that the FFR calculate with our method non-invasively is 0.92, which is very close to 0.93 that we got invasively in the cath lab. So I think the message that I want to bring to you based on this example is that this patient could have avoided the invasive catheterization procedure if a non-invasive tool like this one was used at the first place as the gatekeeper. So I'm thankful that a number of top institutes and hospitals are interested to test this new technology further. So we have successfully applied a CIHL grant to conduct an international multi-center study in order to determine the diagnostic accuracy of this new imaging technology on a larger number of patients. So in conclusion, I have presented to you a new imaging technology that can be used for non-invasive and rapid functional diagnosis of coronary artery disease. And as I said, this technology can be easily extended to apply in other cardiovascular applications. And maybe we can talk a little bit more in the breakout room. Thank you so much again for the opportunity to present to you.
Thank you very much, Aaron. Please welcome Kyle Jackson, PhD student and inventor at McMaster's Chemical Engineering Department in the lab of Dr. Zainab Hosseini Doost, who will be speaking about their technology focused on antibacterial phage hydrogels.
Awesome. Thank you very much for the introduction. Let me just go ahead and share my screen quickly. Can you see my screen?
Yep.
Awesome. All right. Hello, everyone. Again, my name is Kyle Jackson. I'm a PhD student at McMaster University, and I work with bacteriophages, which are viruses that are able to kill bacteria. And with this, we've been able to actually develop a novel soft bond material that is able to target and kill bacteria, which I'll get into now. So to begin, why are we doing this? And to be blunt, antimicrobial resistance, something that many of you might have already heard of, continues to be a growing public health threat. And by that, I mean many bacteria that we commonly, as humans, get infected with, are being able to resist very commonly used antibiotics such as penicillin or ampicillin and amoxicillin. So very, very commonly used clinical antibiotics. And so a few years ago, I think it was 2017 or so, the World Health Organization released a, for lack of a better description, frightening report, estimating that by 2050, estimated 10 million people will die every year that is directly associated with these antimicrobial resistant infections. And that would actually make it the leading cause of death worldwide, surpassing that of cancer and heart disease. So it's quite a staggering number. And although many of you might think, oh, that's in 2050, that's far off, this is an issue today, notwithstanding the current COVID-19 pandemic as well. As in just recently in 2019, the Centers for Disease Control in the States estimated there was over 2.8 million infections in the United States alone that were directly antimicrobial resistant. And that was associated with over 35,000 deaths in the United States alone. So it's already an issue presently. And with COVID-19, with the pandemic, a lot of clinicians and researchers and epidemiologists have actually found that this pandemic has exacerbated the AMR crisis because in the early days of the pandemic, a lot of concerning reports came out of Southeastern Asia and India specifically, where a lot of clinicians were actually prescribing antibiotics to try and treat COVID-19 infections. And because there's actually no infection to deal with, that just promoted the more production of these antimicrobial resistant pathogens that we now need to deal with. So this threat of 2050 is probably much sooner than we actually think. And so this will be a crisis that will disproportionately affect regions of the globe. So yes, we'll have quite a number of deaths in North America a year, approaching around 400,000, but the majority of the cases and fatalities from this rising global pandemic will actually be in Africa and Asia, especially seeing probably about 80 to 90% of all those potential deaths. So this does two things. One, it really demonstrates the fact that countries that have lower socioeconomic statuses and inaccessibility to conventional antibiotics and antimicrobial treatment strategies require novel solutions in order to combat this growing problem that many more established Western countries have really fomented. But this also presents unique market opportunities for innovators that are actually looking to penetrate this antimicrobial space. And so what do? We use the natural predator of these bacteria, so bacteriophages. These are viruses, and they're not bad viruses that you might think of influenza or right now coronaviruses. We classify these as good viruses, and that's because they, as I said, are able to naturally kill bacteria. And there's a lot of enticing properties of these bacteria-killing viruses that make them really good either therapeutic solution or building blocks for naturally antimicrobial materials. So one of those properties is that, again, they're the natural predators. They are extremely selective in terms of their ability to kill different types of bacterial species. In fact, they are able to identify their bacterial target in a heterogeneous mixture of bacterial populations. So you'll have decreased chances of off-target effects that you might experience with conventional antibiotics. Another really key enticing component of bacteriophages is that they are what's known as an active therapeutic. So their therapeutic potential increases as it interacts with its target, cell. So it is able to replicate at the site of infection, thereby increasing its therapeutic efficacy. And probably the most enticing property of bacteriophages is that they are much less prone to developing resistance compared to conventional antibiotics. And that's because these are viruses, so they are arguably living organisms. And so because of that, they're able to evolve naturally with their bacterial target, because a virus's sole objective in life is to survive, and in order to survive, it must evolve with its target bacteria. So what have we done with this? Well, we have kind of leveraged this natural antimicrobial capability of these viruses, and we've designed these viruses to assemble into a biomaterial, a soft biomaterial. So we actually were able to develop the world's first biomaterial that's made entirely of these bacterial killing viruses. And this is a patent pending technology. We have filed a PCT for this, which is great. And this has incredibly far-reaching applications that will impact a wide range of human health applications. And so kind of just a quick demonstration of this just naturally antimicrobial property. So you see on the left-hand side here is an example of one of these biomaterials. So right now it's over top of a lawn of bacteria. And this entire halo around it demonstrates the natural antimicrobial capability of these gels. So all we did was we put this gel on top of a saturated surface of bacteria, and we were able to demonstrate that these very noticeable halo effects is the ability of that material to actually kill those bacteria that the material is on top of, which is quite impressive. So this is a lawn that is not supplemented with any antibiotics. This is just the bacteriophages and just the biomaterial. So it's quite impressive at its ability to kill these bacteria. The other cool thing about this bacteria, about this material itself, is that it's able to self-heal. So if we go ahead and cut the gel in half and then kind of put them together in the same vicinity, they will naturally come back together and heal itself. And if we rotate that 90 degrees and cut again, we see that natural annealing as a material itself. So that also increases potential applications of it, especially as a wound dressing, for example. And so this kind of, we've developed this technology at an interesting point in the global market trends for antimicrobial and antibacterial compounds. Currently, as of 2018, the estimated market cap for antibacterial compounds was about $38 billion. And by 2030, it's estimated to rise up to $55.8 billion, which is associated with a compound annual growth rate of about 7.8%. So in biotech and pharmaceutical terms, that's actually quite a large annual growth rate. So there's a lot of opportunity here to actually penetrate the antimicrobial market with novel strategies to kill these ever-growing antimicrobial resistant pathogens. And so key drivers in this market fluctuations include aging population, where more individuals become more susceptible to these bacterial infections. Again, those developing markets in the Asia Pacific regions and Africa, as well as the emergence of other infectious diseases and other biological threats that are threatening our modern society. And so here are a few reference documents I encourage you to look into if you do want to work with us. We have published numerous publications on these antibacterial gels, as well as done numerous interviews with CBC and other local news stations. So I encourage you to check this out for more information. And on behalf of the research team, I look forward to speaking with you, as well as my colleague Lei Tian, who's in the audience as well. And we'll be happy to answer any questions you have about our technology. Thank you very much.
Thank you very much, Kyle. I would like to now invite Dr. William Altenhoff, professor at Department of Mechanical, Automotive, and Material Engineering at University of Windsor, who will be speaking about his technology, Kinetic Energy Dissipation System.
Okay, good afternoon, everyone. I hope you can all see my screen.
No.
Not yet. Let me click share. Excuse me, that may be one reason why.
Yeah, I can see it now.
Okay, perfect. So first off, thank you to everyone for taking an opportunity and some time to really, what I say, I call myself the lead inventor here, but the reality is it's the efforts of many individuals over many years that have resulted in this, what we really believe, a novel and far better than the state-of-the-art kinetic energy dissipation system, which maybe initially at front thought may not sound too exciting, but you start seeing real quickly when you start looking into some of the data and the impact that injuries and accidents cause to humanity. It's quite significant. So anyways, thank you again, and we will start off here with a little bit of just some information on really energy absorbers and the general problem that we're dealing with. Probably everyone is familiar with some form of an accident, an injury, an explosion, or an event where something very dynamic and traumatic has occurred. Here I provide to you a number of examples, whether it be rail derailment, a vehicle crash, a frontal offset crash, airbag deployment, you see it there. All structures, especially those that are typically contained within earthquake zones, have to have suitable energy dissipation devices to dissipate the seismic energy that exists when an earthquake occurs. Also, fall arrests for individuals who are working at high elevations. They have to ensure that they're using equipment that will dissipate the energy if they fall in the case of an accident. I also provide some examples in the military here of some form of an explosion device, an improvised explosion device, where you can get an idea of the amount of energy that is released and really the trauma that it can impose either upon structures or more critically to people. And just so that you have an understanding of the economics of this, fatal and non-fatal crash injuries kind of over the period of 15 years we measure this in trillions of dollars. On an annual basis, typically just accidents associated with vehicular injuries cost Canada about $24 million. In the United States, it costs about 10 times that much, on the order of $250 million. And the reality is it's a significant problem, and one that we believe we can make, no pun intended, quite a big impact to. A lot of these problems that you see here, they will all involve some form of a mechanical entity or a structure really to dissipate the energy. Maybe something as simple as some beams, some extrusions. In this case, we see some form of a hydraulic damper, some form of a stitching. But ultimately, in all of these entities, we get what we refer to as when we look at their performance, a force deflection curve. And the typical response is one where we see this curve kind of oscillate or fluctuate during the deformation process. So this mode of load and deformation is really not desired. What we would like to see is basically a constant load, one that can be well designed for and well achieved. And I point this out that really this gap in performance is really what's causing a lot of these injuries and the concerning problems that we're seeing. The big thing is certainly there's the economics behind it, but the other thing is really the emotional losses that we experience and the loss of our loved ones and ones we care for. So what we've come up with is really, in our opinion, a very simple, elegant, and it's quite interesting in the sense that how you can adapt it and adjust it so much. We basically utilize a sacrificial material, a sacrificial tube, and what we refer to as an end-bladed cutter. This end-bladed cutter, in this case here, contains 4 cutters. And the purpose of this cutter is really to just slice through the sacrificial tube. Now, the sacrificial tube that we've generally been studying has been aluminum extrusions because they are lightweight, they're recyclable, easily attainable, but you can look at wood as a material, plastics, composites, many types of materials as a potential sacrificial material to dissipate energy. And effectively, we take the cutter, we take the cutter and we slice through this sacrificial tube. The nice thing about that is in the slicing process, you can get quite a flat, or if you will, a kind of a non-varying load deflection curve. The other beautiful aspect to this is you can design it quite nicely to specific loads. And depending upon the number of cutters you utilize, you can adjust the load accordingly. So it has a lot of very nice design aspects that can be altered and tuned for certain types of applications. And again, because of the efforts of many of my past students and current students, we have design equations which we've developed that will predict with very good accuracy the cutting forces that will occur for a certain cutter configuration, a sacrificial tube and material. So here I want to provide to you some high-speed photos that we have from some of our testing that we've done, just so that you can get an appreciation for the differences in the loads that occur during the test. So we're looking at 80-kilometer-hour impacts with a roughly, sorry, I'll use the US Imperial System units here, about a 20-pound bullet traveling at about 80 kilometers per hour impact. This will give you about the energy of a low-speed car crash. And you see on the bottom with the red text, the axial crushing process, the force deflection curve that is generated in the process. You see how it fluctuates. It first has to go up to a high initial value to initiate that crushing and deformation mode, and how it fluctuates over the displacement domain. But for the cutting process, it's quite consistent in the sense that after it passes through some initial transients, it's quite stable in terms of a constant or almost constant reaction load. And that continues on for the almost pretty well the entire crush distance, could be for the entire extrusion length. So the other beautiful aspect to this is if you get wise and support the energy absorber appropriately, you can actually perform or you can perform these energy absorbers in either a compression loading condition, as you see kind of with the, excuse me here, the blue arrows, where we're actually crushing it, or under a tension load. Now, a lot of testing conditions will, the far majority of them, I'd estimate probably 80 to 90% may see tension and compression. So we believe that we have a technology here that has a significant application to a very broad range of applications. Now, the other thing that's quite interesting is we've tested it under, you've seen 80 km/h impacts. We've tested it quite slow, crushing it quite slowly. So on the order of about less than a meter per second, on the order of maybe we would use millimeters per second to quantify those speeds. But we've also tested it with our colleagues from the University of Cape Town under blast loading conditions, where effectively we've put a PE4 charge on the head of the extrusion, detonated that bomb, and then at very fast speeds on the order of 200 meters per second, accelerated the tube through the cutter and assessed its performance with basically similar stability that we've seen in other cases. So we know that we can perform at a wide range of events, whether they be quite slow or quite fast. The other thing that's really beautiful about this system is if you would take your sacrificial dissipator and reduce the thickness, what you can do is you can actually program or alter the load deflection curve to requirements that you may desire or need for a certain application. So this is actually something that a lot of energy dissipators, in fact, far majority of them, cannot do. So this concept of really a passive adaptivity, so the ability to adjust accordingly is again a very elegant aspect of this energy absorber. We are also working on, and we've proved that you can actually develop and use an active energy dissipation system. So we have systems where we can change the numbers of cutters dynamically, very rapidly, and correspondingly, depending upon desired inputs that we measure, we can adjust the force deflection curve accordingly and our energy dissipation associated with that. So I wish to thank you for your interest in this. You know, the one thing I always tell individuals is that, you know, and this is how it is with all researchers. This is, in our opinion, it's very simple, it's very elegant. It has a lot of flexibility for a broad range of applications. And ultimately, our desire is to see such technologies to be used to ultimately better benefit humanity so that we can reduce injuries, we can reduce deaths that are associated with accidents, as well as the significant financial burden that we all bear as a result of those accidents. So thank you very much.
Thank you very much. I would like to invite Dr. Vivek Maheshwari, Professor of Chemistry at University of Waterloo, who will be telling us about advanced perovskite films and crystals for stable energy harvesting solar panels.
Thank you, Susan. I hope everyone is able to hear me.
Yep.
First of all, I would like to thank all the organizers and the sponsors of this event, and of course, the students who are taking the time to make this event successful. What I'm going to do is I'm going to share my screen and play my presentation, which has been recorded as a video. So if there's any glitch, please let me know.
Okay. Are you sharing?
Yes, is it?
We can't
Oh,
see
yeah.
your screen.
Sorry, let me try that again. Are we good now?
Yep, I can see that. Is it animated? Because it's. We don't hear anything.
Sorry. I think probably the video is not playing, so I'm going to start and present it.
Okay.
Let me just do this. Sorry about this. Sorry about the glitch.
Yeah,
Just trying to stop this.
technology.
Yes.
We can see your screen now.
Okay, so let me start this.
Yep.
So good evening and good afternoon, everyone. My name is McMaster, and I, along with Syed Bagari, my colleague, we are going to present here to you a new exciting technology that we have developed at the University of Waterloo that basically leads to development of a new kind of solar cell. We are all aware of the COP26 conference that is taking place. And ultimately, we are aware that as a society, we have to move towards a carbon neutral economy. And we are aware that this cannot be done in a single step, and rather small little steps and multiple steps are needed to reach that point. And to do that, we know that we have to transition from fossil fuels to more renewable energy sources, and the primary ones being wind, hydro, and solar. And if you look at all these sources, they have their challenges in the fact that they are intermittent in nature. Geographically, they have a non-uniformity in distribution. So because of this, all three of them become key players in terms of applying them for developing a potential carbon neutral economy based on renewables. Oh, and that is why, if you look at so that is why all three of them have to be applied, and among them, solar is of course one of the key renewables that has to take place. And solar is key for multiple factors, and among them, you can look at solar that because of its low initial cost, you can develop solars as either as a big solar plant that can generate enough power to power a whole city or a big city block, or even in undistributed and isolated systems where they can basically power up a single house or a single dwelling. Right? And combined with this, the other important factor about solar is that even if you look at a country such as Canada or Ontario, we know that we are quite north of equator. Even then, Canada and Ontario by itself is the top 10 solar market in the world. So we can imagine the potential of solar if we look at countries such as China, India, or Sub-Saharan Africa, where solar energy is prevalent in much more high density and uniformity over the course of the year. And that is what makes solar a key player in this whole renewable energy ecosystem. Now that is fine. Then this is fine. And the key part that is coming up, we already know that solar has been applied for a few decades now. And silicon solar cells specifically dominate this ecosystem. So more than 90% of the solar market is captured by the silicon solar cells, which is fine, right? Because that is where we want to be. We want to generate solar energy. But there is a challenge in silicon solar cells. And the key challenge there is that silicon per se as a material, and as a consequence, silicon solar cells are energy intensive to produce. And a simple way to look at this is, if you look at the amount of energy that goes into producing a silicon solar cell, packaging it into a panel, taking that panel and basically installing it either on your rooftop or installing it on your rooftop, or installing it in a big solar farm, the total amount of energy that goes into that process, around slightly less than 50% of that just goes into producing these silicon solar cells. So they are highly energy intensive to produce. So to gain more advantage of the silicon solar energy or the solar energy, we have to reduce this energy footprint of producing these silicon solar cells. And that is where we are, that we want to basically go ahead and present a solution that is based on perovskite-based solar cells. Perovskite is a recent class of materials that have come up in last 10 years. And already perovskite-based solar cells rival in efficiency those of the silicon solar cells. So efficiency-wise, they are pretty comparable to silicon solar cells. The key advantage of perovskites is that they not only that they have high efficiency, they are very easy to manufacture. They are low cost, and they are very less energy intensive compared to silicon solar cells, almost a fraction less. So this is what makes perovskite solar cells a new kind of solar cell that will further advance us in terms of capturing the advantages of solar cells, that you are able to basically generate free green energy. So this is all fine, but then why are we not seeing the implementation of these perovskite solar cells on a larger scale? And that is where we present our technology. That if you look at the current state of perovskites, the biggest challenge that perovskite solar cells are facing is that they suffer from long-term device stability issues. What that means is that if you take a perovskite solar cell, the perovskite material inherently, a pure perovskite material, is not very stable. So if you apply a voltage or expose it to air, specifically oxygen or humidity, the material starts degrading. So as a result, the lifetime of these cells is very limited. And that is where we present our solution. That we have developed a class of composites where we mix perovskites and a commodity scale polymer to basically take these perovskite materials and make them highly stable. The advantage of this is that not only we increase the stability of these perovskites to the extent that they are almost comparable to silicon, but the other key factor is because we use a commodity scale polymer and we don't add any extra manufacturing steps, we maintain the advantages these perovskite solar cells have over the silicon solar cells. That basically, they are easy to manufacture, they require very less energy to do so. And that is why we are so excited about this technology in terms of presenting it and bringing it forward to the market. In terms of where the application of these perovskite solar cells can lie, it will be not just in the typical markets for the not just the typical solar cell markets, but also places such as niche markets, such as in rural areas, remote areas. And because we can make them into a flexible panels also, the next important application would be in high density city cores over things such as curved building facets, and even other niche markets such as space technology. So that's in a short is our new technology that we have developed. And I, along with my colleague Syed Bagari, will be happy to answer any questions that you may have during the discussion session.
Thank you very much, Dr. Maheshwari. I think we can move to our last technology, and I think I would like to welcome our master student and inventor, Timothy Mills from University of Guelph, who will be talking about his technology titled Portable Temperature Controlled Storage System.
Okay, thanks, Suzanne.
Are you sharing your screen, Timothy?
Okay, I just stole the screen share there.
Okay.
Okay, so I'm going to just start with a CAD model of what we have designed, me and my co-inventors. So this is a thermos that has been equipped with a small refrigerator. So it can be used for vaccine transport in remote locations that are off grid. And the key innovation that we have brought is thermal decoupling. So if you see here, this is representative of the thermoelectric cell. That's like the heat pump in the system. And if we unscrew the cap, we create a vacuum area. And this thermally decouples the inner contents of the flask from the exterior. So this allows you to cycle the refrigerator on and off, which has big implications for its efficiency. So if we go to, so this is the prototype that we built, and you can see on the right, we didn't actually build the vial holder for the vaccines, but this is representative of what a vial holder might look like. So, or it's representative of the thermal properties that a vial holder would have. So that's why we just stuck a big piece of copper on the end. And then here were our performance, I guess you'd say, of our experimental performance results from that prototype. So things to note: at very low temperature differences, 6 degrees, the highest heat removal rate from the flask was achieved with the lowest power input. And at higher temperature differences, so that's when the inside was very cold, you have to really dial up the power consumption to achieve any sort of substantial heat removal. And just to visualize the benefits of being able to decouple versus a system where there's a solid thermal connection between the inside of the flask and the exterior, I have this chart. So this assumes a lot of things, like a fixed battery size of 111 watt hours, or that's a 30 amp hour battery at 3.7 volts. And it assumes an interior temperature of 5 degrees Celsius. But you can see at low temperatures in particular, decoupling and that cycling on and off really boosts your efficiency. So as opposed to being out in the field for 3 days roughly, and then having to recharge, you're able to stretch that to 14 days. Again, given that battery pack size. And the graph would be linearly shifted up by a factor of 2 if you doubled the battery pack size, or all the points would be, you could divide them all by 2 if you only had 15 amp hours. Another thing to note is that if you got a more powerful thermoelectric cell, this convergence point would be shifted to the right. The convergence point represents the temperature, the external temperature at which the thermoelectric cell has to be operating continuously to keep that inner flask temperature at the 5 degrees required to keep vaccines to preserve vaccines at that 5 degree point. So after roughly 35 degrees ambient temperature for this setup of flask size and TE power, thermoelectric power, after that point, the decoupling makes no difference. So if you were going to be operating in climates that had this, you'd probably be advised to pick a larger, more powerful cell where you could still get the benefits of the cycling on and off. So yeah, this is our technology, a little bit shorter presentation, but if you have any other questions, we'd love to chat with you in the breakout rooms, and yeah.
Okay, thank you very much. Well, you kept us on time. Thank you.
No problem.
I just want to thank all our inventors for telling us about their exciting research with the potential of becoming future products that are solutions to real problems. We're looking forward to the creativity that will be sparked by the competing teams in coming months. At this point, I'd like to invite Dr. Leslie Rigg, Western University's Vice President of Research, for closing remarks. Leslie?
Thanks, Suzanne, and thank you, everyone. Good evening. I guess it is almost evening, 2 minutes and it's evening, right?
Yeah.
So thank you everyone for joining us at this year's launch of the Proteus Innovation Competition. I really hope you're as energized as I am. I know that I've learned a ton already about this year's partnered technologies, and I'm sure there's going to be lots of great conversation in the breakout rooms. So seeing ideas and projects come to life is really one of the most rewarding aspects of what I do as a VPR on a daily basis. It truly never gets old. I get super excited about coming to events like this. And I love seeing new members of our communities bring different perspectives to engage, not just with these projects, but to provide their own ideas. And really, we hope that the group together in the community will take it all to the next level, right? That's our desire. You know, I really believe that curiosity is our inner driver. And curiosity, creativity, and the fundamental desire that we have to discover. From the foundation of innovation to the core of our ability to improve lives. Innovation helps improve health, culture, societies. It's really how we mobilize for impact and take steps towards progress. So I applaud you for taking the opportunity to stretch beyond your comfort zone. For some of you anyways, and to gain new skills and experiences, and to potentially find some new mentors through this competition. Relationships are key, so those mentors are really important. I'm always particularly pleased to see how Proteus has grown to leverage the skills, to leverage mentors, to leverage technologies from not just here at Western, but from all of the universities that are participating across Ontario. This collaboration really allows us to build relationships, to think bigger, to think differently, and really to support our collective success. So, and this is really important at this point in time, because our world is shrinking. Our interrelated research, entrepreneurship, and technology development ecosystems no longer adhere to traditional boundaries, as we're seeing today as we're doing this on Zoom, right? In fact, I would argue that Western's entrepreneurship ecosystem, which includes initiatives like this competition, may in fact be less about the products that we create and more about the people and the developing of an innovative and entrepreneurial mindset in those of you that are taking part and those of you that you rub that off on, right? Because it's not just about the people on the screen today, it's about the people who you talk to. It's about providing unique interdisciplinary approaches to discovery, where we bring together people from different backgrounds to tackle challenges in new ways. It's about fostering a belief that every member of our community, whether they're faculty, students, staff, postdoctoral scholars, donors, friends of the university, alumni, community members, it doesn't matter. Because what we want to do is develop entrepreneurial thinking that should be afforded, and all of those individuals should be afforded that opportunity. This is nothing new at Western. By combining our strengths with the energies of those who have the ideas for changing the world, that's you, we have long worked to erase the notion that a university's mission runs counter to entrepreneurial ambitions. It couldn't be. Entrepreneurial ambitions are at the core of what we do. I have often in the past linked the scientific method to entrepreneurial thinking, and so maybe at some point in the future we can chat about that. I believe you're going to see even more of this mindset taking root in coming years. As we roll out a new innovation and strategic partnerships portfolio here in the Vice President for Research Office, that portfolio will support researchers, scholars, and artists. And we are also going to begin to implement the new vision for our research parks here at Western. So all of that's to come, and I can't wait to share much of it with you. In closing, though, I would particularly like to thank the World Discoveries team for stewarding and growing this program for the past 7 years. And I know that's been said earlier this evening, but I'd also like to express my appreciation to the mentors who are here, to the inventors, to the innovators, and for those who take all the time to share what they do with us, including the technologies that you brought forward today that we've just listened to. So good luck to all of you competing in this Proteus competition this year. I really can't wait to come back in a few months and hear what you've done. It's really exciting. So thank you for having me. Thank you for letting me listen to what you're doing, and looking forward to what the future holds. Thank you very much.
Thank you very much, Leslie, for your closing remarks. I have to say it's really exciting, and I know that this is an opportunity for all of the tech transfer offices that are collaborating together to really engage with a much wider community of students and faculty. And it's always been fun, and I'm looking for another year of it. It's been fantastic. This brings us to the end of the formal part of the event today. I'd like to thank again the university partners, sponsors, speakers, and inventors for coming to our event today. Please note that we will open the breakout rooms for each of the technology, where you can actually navigate each breakout room as you please, and get a chance to speak with the inventors and the business development manager that will be supporting you over the next 4 months for the technologies. Please make note of the important dates to remember. January 10th is the last day to submit the abstract. That's where you have to have your teams together to submit your abstract. And January 20th is the business plan workshop.